Hello, I am Pete Demar with Battery Research and Testing, and in this session of our stationary battery maintenance tech tips, this is tech tip number 8, accurately measuring float current. In here, you will be shown how to accurately measure that float current. This video was created by Curtis Ashton, and I first saw it early 2019, and because he did such a good job in down-to-earth language explaining this, I asked him if I could use it in one of our tech tips. He agreed, and so here it is. Curtis has over 30 years experience in the DC power field and has worked with batteries from probably as low as 50 amp hour to 4,000 amp hour, and with central office plants where he must have had over 20,000 amp hour of battery installed. His involvement covered battery systems from 24 volts to 480 volts, and from outside little communication boxes to large central offices across many states. He also presently is the chairman of the IEEE PES ESSB. That stands for the Power and Energy Society, Energy Storage and Stationary Battery Group. That group is responsible for all stationary battery-related IEEE documents. So without further wasting any time, here he is.
We're going to take a DC float current measurement, and at first I'm going to try using a standard AC-DC clamp-on ammeter that most technicians are equipped with. It's important that it says DC. It's a special measurement method for measuring DC versus AC. So you can see that this one says DC, and also there's a setting for measuring amps DC. All DC measurements need to be zeroed before they are taken for a clamp-on ammeter. So this one's now at 0. The way this meter is zeroed is simply by turning it off and then turning it on again. It's how to zero this one. Others have a button. So here I can take my measurement anywhere in the string because current in a series circuit is all the same no matter where I take it in the string, per Ohm's law and Kirchhoff's laws. So my problem is my jaws aren't going to fit around any more than 2 cables at a time here. So I can either take 2 measurements of the 4 cables, the ones closest to me and then the ones furthest away, or I can assume that they're going to be equal and take 1 measurement and add it up. So here I'm going to take 1 measurement, and you have to make sure the jaws are closed. And this tells me that I've got 0.1 amp. It's jumping between 0.1 and 0.2. So that tells me that between 0.1 and 0.2 here is how many amps I have. That's about 100 to 200 milliamps. Now if I double that, because I've got 2 sets of cables, I'm going to have somewhere between 200 and 400 milliamps. Using the IEEE 1635/ASHRAE 21 standard, or the calculator that's freely available on the IEEE PES ESSB website, I can determine that these 1600 amp hour pure lead round cell batteries should have about 100 milliamps of float current. So you can see that this standard meter is not really very accurate. It's not accurate enough because it's only measuring down to tenths of amps, and I need to be measuring milliamps. Alright, so I'm going to turn this one off. I'm going to use a specialized meter with a small jaw. This is rated only for 30 amps maximum. And so this little tiny meter here can measure DC or AC, small currents. Oh, sorry, it's a 40 amp maximum meter. The problem with it is that when you try to buy meters like this one, the jaw opening size is not very big. This is a 7/8 inch jaw opening, which means that the biggest cable it can possibly fit around probably is a 4/0 cable. These happen to be 4/0 cables, thank heavens, and I'm only going to be able to get around one of them. So I'm going to turn the meter on, I turn it to the DC setting, and it almost zeroes out. In this case, well, now it's jumped up, but before I zero it, there's an auto zero button right here that you can see. I come up close to where I'm going to take my measurement. I hit the auto zero button, and then I clamp around the measurement I want to take. Alright, so I've got it clamped around a single cable, and it's jumping anywhere between 32 up to 48 milliamps. Actually got down as low as 24 there. I expected about 100 milliamps out of this string, so if we take an average of 40 milliamps, that's 160 milliamps, because I have 4 cables here that are equal in length and equal in resistance. So I'm seeing about what I should see for this type of battery. Here we have a mini cake battery string. So in this case, the small clamp-on ammeter will not fit around these big 350 kc mil cables. There are a couple of meters available on the market that have a 1-inch diameter, which might fit around some 350 kc mil cables. Or it might fit around an intercell strap that's 1 inch. You can see on these that the intercell straps are 2-inch straps, and so I can't even go around those with the jaws of any of my meters. Nope, can't get around it with this one, I don't think. Nope. But I can get around the cables, 1 or 2 of them with this larger clamp-on ammeter. But remember, this is not going to be accurate, because out of these strings I expect to see about 500 milliamps or a ½ amp of float current. If I'm only doing 2 of them at a time, that'll be about 250 milliamps through the 2 cables. And I can't even get around 2 of them even with this larger jaw. So I'm going to have to go around 1 of them and multiply by 4. Okay, and it tells me I forgot to zero it, so we're going to go again, turn it off, to zero it. That's how this meter works. Make sure we're at 0. There we are at 0. Then we clamp it. And we have 0.1 amps, somewhere between 0.1 and 0.2 amps, 150, let's call it 150 milliamps times 4 is 600 milliamps, which is about what we expect. You can see that it's very difficult at low current ranges to get a good accurate reading of DC float current. 12 volt monoblock VRLA lead calcium AGM batteries, they're small, so the float currents are small as well. I'm running the numbers through, we're looking at the manufacturer's data, we're running the numbers through the IEEE 1635 guessing calculator. Tells me that my float current on this 46 amp hour string should be somewhere around 50 milliamps. On the 30 amp hour string that we're going to measure after that, it should be somewhere around 35 milliamps or so. So I've got my clamp-on DC ammeter again, my small jaw one, and I'm going to zero it before I take the measurement, and then I'm going to clamp it around, and I'm measuring 10 milliamps, which is excellent. These batteries are in excellent shape. It's well below what's expected. Like I said, 50 milliamps is what I expected. It's well below that, and that's good. These batteries are, I look at the date code on them, they're a little over, well, they're actually 3 years old. So they're fairly new. They're sitting on a good telecom charger. Now when I measure this 30 amp hour string, this is a 10-year design life battery, and it's actually 12 years old. So I'm actually expecting more than what it's supposed to be. As we said, it should be around 35 milliamps of float current. If I zero it here and then clamp it, I'm actually getting 160 milliamps of float current, which is more than 5 times what I expected. These are in the beginning stages of thermal walkaway, which is not surprising given that they're 12 years old on a 10-year design life and a 7-year expected life. Okay, here we are in front of a UPS UPS, there are two different types of current measurements to take at a UPS, DC and AC. So the DC float current is similar to what we've already seen. This is a 400 watt per cell UPS type battery, 12 volt monoblock, and the expected float current from the manufacturer and IEEE is somewhere around 100 milliamps of DC. So I'm going to take my small clamp-on DC ammeter, I'm going to zero it, and I'm measuring 33 milliamps. So it's less than what I expected, which is good. It means the batteries are good. These are fairly new batteries. They're doing well. So that's the DC float current. Now for the AC. This meter, you'll notice, this meter says AC, but when I try to measure AC with it, bouncing all around, but tells me about 39 milliamps. We're going to prove later that that's incorrect. And the reason is that you'll notice that this meter does not say true RMS. The AC current, the AC ripple current that's imposed on a UPS battery is typically much higher than 50 or 60 hertz. This meter is meant to measure currents, AC currents with a frequency range of 45 to 65 hertz, and we'll see later with a different type of meter that the frequency is much higher than that, being imposed mostly by the inverter on this UPS. This UPS is 54% loaded. So now I have a true RMS AC/DC meter, and so I'm going to go ahead and set it to the AC setting. It's not zeroed, so I'll turn it off. Turn it back on, and I still can't get it to zero. As I was preparing for this video, what I learned, you can see here that I'm not even clamped around the cable and I'm already measuring 28 amps. The problem with many UPSs, this one has on the DC bus, it has a 15 kilohertz switching pulse width modulated DC to DC converter. And that puts a lot of electrical noise into the system. This is not the most expensive AC clamp-on ammeter out there, and you can see as I move away from the noisy environment that the current drops off. So I can clamp around this cable, but it's not an accurate reading because there's too much noise in the environment. This particular meter is probably accurate. When it says true RMS, it's probably accurate for somewhere between 50 to 1,000 hertz or 50 to 500 hertz. And we'll see later on that the AC current in this one is at a much higher frequency. And we'll go into that in a minute. Okay, we're going to talk about the effect of AC ripple current on UPS batteries. And this is an average graph. There's been some research in this area, not a lot. What the research shows us is that AC ripple current imposed on the DC bus by mostly the inverter, but partly by the rectification system, once it gets into a couple hundred kilohertz, it has no effect on the battery. It acts as a capacitive charge on the plates. The electrons don't have time to penetrate the plates before they turn around and head the other direction. So it acts more like a capacitive charge and does not really damage or heat the battery. However, today's technology, to get to that kind of switching speeds, you need high bandwidth, high band gap switching frequency semiconductors, which is not silicon. It's either going to be silicon carbide or gallium nitride. Eventually, UPSs will be made with that technology because it's more energy efficient. You can get your energy conversion efficiencies up higher, and as people search for improved energy efficiency to save money, they'll go that direction. But right now there's about a 40 to 50% cost premium to pay for that kind of switching frequency. This one I said was switching in the range of about 15 kilohertz, which is down here, which corresponds on this graph, and it depends on load and the magnitude of the current, to about a 20% decrease in life of the battery at that kind of a switching frequency. You can see down at 60 hertz, I'm at more than 50% decrease in life. So this is a logarithmic graph. The lower the frequency, the AC frequency, then the higher the damage to the battery. I was not able to measure it with a standard clamp-on ammeter, so I'm going to go to a specialized meter. It would be best if I could use a scope meter, but I'm going to use a power quality meter that's capable of measuring up to 10 kilohertz easily. As you can see, most of the damage is done to the battery in that range below 5 kilohertz or so. What we have here is a power quality meter that's capable of measuring frequencies up to 10 kilohertz. I'm going to concentrate on the first 64 harmonics, which is up to about 4 kilohertz. So if I wanted to measure above that, I would need an oscilloscope with coaxial inputs. This doesn't have that. So here I am, and you can see that there's a measurement going on right now. This is the AC current on channel A, but you can see here that I've got nothing hooked around it, but it's just electrical noise. Here we're dealing with less than 50 milliamps of electrical noise. So when I hook it around the battery cable, it's important to note, come on over here, it's important to note that I hooked it around the middle part of the string. Up here we have our big DC breaker. I don't want to get anywhere near that with the safety gear that I've got on, or the lack thereof. That's 540 volts DC at the top. This is a floating ground system, so I do not have to worry down here except for about 12 volts. Reading now, I'm much greater than 50 milliamps. In fact, it tells me that the signal is probably somewhere close to an amp. It says 1.25 amps per division. If I exit out of this screen to look for the actual RMS value on my meter, it tells me I've got 587, 583, 570 milliamps of AC current, which is almost 20 times what the DC float current was. So you can see that the heating value of AC current can be much greater. However, as we looked at the graph, it's important to note where that current exists, at what frequencies. So with this meter, I can look at the harmonic content. This tells us that our main amount of AC current is at the 58th harmonic. And so, even though I have about 600 milliamps of AC current flowing through this string, which is not a lot compared to many UPSs, because this is a newer UPS, almost all of that current is clear up in the range of around 3,500 hertz, which, as we saw on the graph, is much less damaging to the battery than lower frequencies below 1 kilohertz or even below 500 hertz. So we can see that we're going to lose some life due to the AC current in this, but I'm at a higher frequency, so the effect's not going to be as bad. Okay, this is an older UPS. That means when we get to measuring the AC, the frequency will be lower because the newer the technology, the faster the switching, which obviously is better for the batteries as they build that inverter sine wave using voltage modulation technique. So first we'll measure the DC float current. These are 300 watt per cell batteries. So the flow current I expect from the manufacturer from IEEE hash rate 1635 standard, somewhere around 70, 60 milliamps, 50 milliamps, somewhere in that range. So I've got my DC flow current, I zero it, and then I measure it, and I'm at about 40 milliamps, which is below where I expect it to be. It's not as good as the previous one, but these are a little bit older batteries. So they're starting to rise in flow current a little. Now to measure the AC. I do wish that I had a smaller jaw. It would be more accurate, but this is the only one that I had that would go do a small current measurement. This one is settable, as we can see from the adapter. It's settable for ranges of 3,300 or 30 amps. And so this one is, I've got it in the 30 amp setting. Now here we can see, here's what my wave looks like, my waveform on that current. It's less than the previous one because the last one auto ranged to 1.25 milliamps per division. This one's auto ranged to 250 milliamps per division. We can look at what the RMS value is here, and it's 140 milliamps as compared to about the 600 that we saw on the other UPS. The big difference is that this UPS is only loaded at 4%. The other UPS was loaded at 54%. The more loaded the UPS is, the harder that inverter's working, producing more and more ripple current on the DC bus. So let's look, we talked before about the harmonics. Let's look at what the harmonics look like on this one and where my trouble frequencies are. So I'm going to go back and set my options properly. Now we see that almost all my bad current, almost all that 140 milliamps is occurring clear down at the worst frequencies. There's a little bit up at the 64th harmonic, but most of it's in the first and second harmonics at 60 and 120 hertz. This older UPS just used older technology as it built its sine wave, and that means that I'm seeing almost 140 milliamps at 60 hertz, which is probably worse than the 600 milliamps we saw at almost 3,500 hertz for the batteries.
It may not be understood by all users, but it is understood by every battery manufacturer and every real expert in this field that the float current that is flowing through the battery string is one of the very first indicators of the condition of the battery. Do not rely on the amp meter on the charging source for this reading. This cannot be emphasized enough. Do not do that. Depending upon if the battery is a vented or valve regulated design, it can provide different information. It is always the very first indicator of conditions that can lead to thermal runaway, though. And yes, vented batteries also go into thermal runaway with the same disastrous results as valve-regulated ones. Because an increase in float current from standard is the very first indicator of a problem, is why we created an Excel spreadsheet that will automatically take 4 readings that you already should be taking during any inspection, and then alert you to danger when flags are raised. That free program is explained in Tech Tip number 11, Excel Thermal Runaway Prevention Program. If you'd like a copy of that free program, just contact us at info@batteryresearch.com and request one. It's a very simple program, but it works. This measuring and monitoring can also be accomplished by having a device installed that monitors those 4 readings and alerts you to changes. Since the float current is the first key reading, the unit must accurately measure to less than 1/10 of an amp. One example of these is a BEM. That stands for Battery Event Monitor. The benefits of a BEM type monitoring service is explained in Tech Tip number 9. Hopefully, this helps provide you with some knowledge that you were not aware of. Please remember that, as Curtis explained, you must zero your handheld meter just before you take the float current reading. This is critically important. If you are interested in learning more about what we do or how we might be able to help you, please go to www.batteryresearch.com and look around. If you would like to be notified when we release a new tech tip, please go to info@batteryresearch.com and tell us to notify you when we release one. Or if you just have a question on a stationary battery subject, just do the same. Oh yes, very important. If you have any experiences or pictures of unusual things that you have found, please share them with us so that all of us in this industry can benefit each other. Have a great day, stay safe, stay healthy, and thank you.